So today we're going to open up with this example. It's just one more solving a triangle example. And some of you may have noticed there's something fishy about this example right away. Don't mention anything. We want to see it happen. We don't want to spoil it for anybody who doesn't see it. We want to solve the triangle, and we're given three sides of the triangle. So we're going to use the law of cosines to solve the triangle. We have the SSS case. So we notice that it's the SSS case. And so we're going to use the law of cosines. Also, we have a 13, a 10, and a 24 centimeter sides, or we have 13, 10, and 24 centimeter sides. And my general strategy is to go after the biggest side or the biggest angle first. So when solving triangles, if you have to pick a place to start, go for the biggest one first. I don't know. It's like prison rules. Just go for the biggest angle or the biggest side first. Let's find the biggest angle first, as our usual strategy. So our usual strategy is to find the largest angle first, and in that case, we're going to find gamma first. So the law of cosines, when solved for an angle, says gamma will be the cosine inverse of a squared plus b squared minus c squared divided by 2ab. So in this case, that's going to be the cosine inverse of 13 squared plus 10 squared minus 24 squared divided by 2 times 13 times 10. And we're going to grab our calculating machine or your book with all your trig values in it. And we're going to look up the cosine inverse of all this. So cosine inverse of the numerator, 13 squared plus 10 squared minus 24 squared, close the numerator, divide by, open the denominator, 2 times 13 times 10. Close the denominator, close the cosine inverse, double check, and hit enter. And we get this error, a domain error. So let's see what happened. Let's see what this looks like. So let's see what this looks like without the cosine. So let's get rid of the cosine, and that means I get rid of this end parenthesis. And the same thing happened here that happened with the no triangles case of the law of sines. We were trying to take the cosine inverse of something that was greater than 1 or less than -1. So what we have now discovered the source of the error. We were trying to do the cosine inverse of negative, that's not a problem, but the 1.18 is a problem. No angle has a cosine greater than 1 or less than -1. No angle has a cosine greater than 1 or less than -1. Cosine of theta should always be always be between and including -1 and 1, not strictly. Let's take a look at the given information and see how we could have seen this coming. Notice that one of the sides is 13, the other side is 10, and the third side is 24. So one of the sides of this triangle is greater than the sum of the other two sides. So note that that side C, 24, is greater than side A plus side B. The largest side, one side, is greater than the sum of the other two. This is a recipe for not making a triangle, because the side A and side B have to make some kind of angle. But if the distance from side A and side B have to make some kind of angle, but if we make a 13 centimeter, and here's the line where the 24 is supposed to go. And a 10 centimeter, this distance between the start of A and the end of B has to be less than 23. Because if gamma is 180, then these 2 points are at most 23 centimeters apart. If I completely flatten out gamma to 180 degrees, then the farthest I can get, the start of A from the end of B, is 23 centimeters. And that third side is greater than that distance. Any questions? So in this problem, you would just, if you didn't notice that, just like before with the ambiguous case of the law of sines, if you didn't notice that there was not going to be a triangle possible here and just proceeded with the law of cosines, you would get stopped in that first step. Any questions? So what I used here to build this knot triangle is what's called the triangle inequality, a concept so important it gets its own Wikipedia entry. And it says, the triangle inequality states that for any triangle, the sum of the lengths of any two sides must be greater than or equal to the length of the remaining side. So the sum of any two sides must be greater than the length of the remaining side. Because if we flatten out those two lengths together, and the remaining side is longer than the greatest distance you can put between the start of A and the end of B, then you won't be able to build a triangle. And at that point, if gamma is 180 degrees, you don't even have a triangle. You just got a line segment. If we push the 24, let's see what happens. What if we drop this 24 down to 23? What happens? We're trying to find the cosine inverse of -1. And the cosine inverse of -1 is 180 degrees. So that's going to tell you right there, there's not a triangle here. It's just a line segment. Because one side is 23, the other two sides are 13 and 10. So the only way to connect all the vertices is to make a line segment. I can't recall if a line segment can be thought of as a degenerate triangle, so I won't bring it up. Oops, I just did. I'd edit that out if I edited my videos. Any questions? A valid question would be just regarding strategy. Usually say just go for the biggest angle first. What if we went for the smallest angle first? What if we switched the role of the 10 and the 24? So if we did, if we put the 24 in for, and then put the 10 in for B, but then instead of 13, it would be 13 times 24. We still get a cosine inverse of something greater than 1. So regardless of which you actually go for, the cosine inverse will be will tell you that there's a domain error, which means no triangle. The ruling on the field will be no triangle. Any questions? Comments? Deep thoughts? How's everybody okay? All right. So there's another situation where we could have a no triangle ruling. It's in the side case where we fail to meet the requirement of the triangle inequality, where the sum of any two sides must be greater than the third side. Remember that in the triangle inequality, the sum of any two sides must be greater than the third side. So you couldn't say, well, 10 plus 23 is greater than 13, so we're okay. That's not satisfying the triangle inequality. There are two sides whose sum is greater than the third side, but any two sides. So you have to pick 13 and the 10, and they are less than the third side. Let's talk about our next big thing. Vectors. A vector is a quantity with a magnitude and direction. That's how we want to think about vectors. When we talk about, it's different than a number like this, 13 centimeters. It's just a distance. So a vector is a quantity with magnitude and direction. So a vector is a quantity with magnitude and direction. We usually denote vectors with arrows. We visualize vectors with arrows. So they're represented by arrows. When we're coming up with names for vectors, we want to make sure that we want to differentiate the vectors from scalars, just magnitudes. So a quantity with just magnitude is a scalar. So a scalar is going to be a quantity with just magnitude to differentiate it from a vector. So the quantity parents are like, oh, listen, scalar, why can't you be more like your sibling vector that has some direction? I wouldn't know. I'm an only child now. I'm just kidding. I have always been an only child. I did not disappear my brother that anyone can prove. Just kidding. I never had a brother. She was my sister. I'm just kidding. I did not have any siblings that I disappeared. All right. So we usually represent our vectors with arrows to point in the direction that they're going. They have an initial point and a initial and a terminal point. I couldn't remember what the words were for a second there. So where it starts is going to be the initial point. And where it ends, we will call that the terminal point. So start and end is what I'll probably say most of the time. To differentiate vector names from scalar names, when we're writing, I'll call this vector, say, v. And if I'm writing, I'll put an arrow over the top of it. An arrow over the top of it is how we will name a vector. So put an arrow above a letter to make it a vector. So the arrow above the V indicates that V is a vector. If our initial points and terminal points have names, so sometimes we name points. So if this vector starts at point P and ends at point Q, we might name this vector PQ, but we still want to indicate that we're talking about the vector PQ and not the line segment PQ. So we use an arrow to indicate a vector. As opposed to the line segment PQ. Putting an arrow on top says it is a vector starting off at P and ending at Q. So we're making a distinction between the vector PQ with the arrow and the line segment PQ without the arrow. This is what we do normally when we are writing. We'll put an arrow above a letter name to indicate a vector. If we are typing, we might just boldface the letters. If we're typing, So when we're typing, we use boldface to indicate vectors. So instead of writing V with an arrow over it, we write a boldface V. And then you can see why we don't do this when we're writing. So when we're typing, the other reason to use boldface is that it's really easy to put boldface on something. It's kind of a pain to put an arrow on top of things. This is even in the age of computers. There's too many steps to put an arrow on top when you can just bold the vector. Even like on a typewriter, you just like hit the V a bunch of times in the same space. But to put the arrow on top of the V, you have to print a whole separate little stamp for your typewriter. Any questions? There's a notation that we use in calculus. See, calculus came up anyway. There's a notation that we use in calculus called prime, where we put an apostrophe after a letter. And this is to indicate the derivative of the function f. When Newton originally made this notation, he said to make f prime, he put to indicate the derivative, he put an f and then put a dot directly on top of the f. And then this is fine if we were writing, but now you want to print this out, and the printer's like, "Oh, dude, I don't have an f with a dot on top of it." And Newton's like, "Oh, well, can't we just make one?" And the printer's like, "Oh, yeah, no, yeah, no, yeah, I'll just do this." And then just put a prime at the end of it, because he did have a little metal piece of an F and then a little metal piece with a apostrophe. So the printer's like, "Oh, nope, I'm going to move that off to the side." Newton also called these fluxions, but I don't know. Probably a British thing, coming up with weird words for stuff. Any questions? Not about fluxions, but about vectors. It's a quantity with a magnitude and a direction. All right. So if two vectors are going to be equal, they have to have the same magnitude and the same direction. So equal vectors have the same magnitude and direction. So let's say this is the vector u, and down here we have the vector v. Both u and v have the same magnitude and direction. U is equal to v. That's bad grammar. U are equal to v. If I have another vector that's 2 squares long, I don't know if you can see the squares, but I have squares here. If I have another vector that's 2 squares long, there's the vector p. The vector u is not equal to the vector p. They're both 2 units long, but they're pointing in different directions. The magnitude of u and the magnitude of p are both 2, but we're pointing in different directions. If we want to indicate the magnitude of a vector, we put super absolute values around it. So magnitude of u is equal to the magnitude of p, which is equal to 2. So that double absolute value is magnitude. Sometimes you'll see just one absolute value. So sometimes we use absolute value on a vector to indicate magnitude. That makes sense because the absolute value of a number is the magnitude of the number, and we ignore the positive and negative parts, which in some sense is a direction. So the magnitude of u and the magnitude of p are equal, but they have different directions. So if I draw another vector over here, let's say q, so notice that v and q are going in the same direction, and also u and q are going in the same direction, but they are not equal. So v is not equal to q. They have the same direction, but different magnitudes. In this case, the magnitude of v, I gotta check your book. Does your book use absolute values or just like the double absolute values? Scrolling. They just use absolute values. The magnitude of v is equal to 2, and the magnitude of q is equal to 1, and those two values are not the same. But they are pointing in the same direction. If I draw a third vector, it's 2 units long, it's purely horizontal, but it's going to point in the other direction. Let's call this vector w. So notice that the magnitude of w is 2, just like the magnitude of u and v, but it's pointing in the opposite direction. So v is not equal to w, but we could say that w is -1 times v. Same magnitude, opposite direction. That -1 turns the vector into the opposite direction. Any questions? So we've introduced this new object called vectors. They're quantities with magnitude and direction. And this is a math class, so we're going to perform some operations on these new objects. So operations on vectors. So here are the operations that we need to perform on vectors. There's vector addition. U plus V. There's scalar multiplication. K times V. K is a constant. Let's say K is a scalar. Let's say that K is, let's just be honest about where we're getting our scalars. So scalar multiplication, multiplying a vector by a scalar. And the scalars that we're going to use are real numbers. And when we say real numbers, we mean real numbers, not that toxic, real numbers don't eat quiche. Not that toxic way. I just mean it's just a real number. It's not the square root of a negative or something. Some quiche eating square root of a negative. Wait, I said I wasn't going to do that. Sorry, my bad. I'm just kidding. Quiche is delicious. What can I say? I'm very complex, but it's all in my imagination. It's probably best that not really a lot of people watch these videos, so all these bad math jokes just can like dissolve into the void. It's really excellent. So these are the two big operations on vectors that we have to get used to. There are others. So I've got vector addition, I've got this scalar multiplication. So clearly I need to separate out different kinds of multiplication. Otherwise I would have just said multiplication and not scalar multiplication. The cool thing is there are two kinds of vector multiplication. One called the dot product, or the scalar product, but that would be written as U dot V, and one called the cross product, which is a vector product, where we write U cross V. So when you're first learning math, you learn X is going to be your multiplication symbol. Then you get into algebra and it's like, all right, we're going to use X as a variable. And you're like, oh, but we were using that for time. Shouldn't we use something else? And the teacher's like, oh, nope, we're not using X as times anymore. So knock it off. And then you get into trig and your instructor's like, oh, dot product. And you're like, oh, yeah. We've used dot for multiplication before. And cross product. And you're like, oh, dude, did you not just tell us to not use that for multiplication because we wanted to use it as a letter? And I'm like, oh, it looks totally different. See how it's just an X with a straight side? And when we write an X, I like hook one of the hooks, hook one of the legs. And the students are like, oh, dude, really? That's the difference? I'm like, oh, yeah. And if I'm typing, I don't have a little serif. It's just like sans serif. See? Very few instances do we just start changing what the symbols mean in math class, and this is kind of one of them. In our defense, we're like, well, let's just do something 5 times 3, and it's like then someone's like, oh, hey, what about this algebra stuff? We should use X marks the spot. X is the variable. And they're like, oh, well, we've already got X as multiplication, but that sounds really cool, so let's run with it. Like I was there. All right, let's talk about how vector addition works. If I've got a vector, let's say that the vector u is going to go 2 squares at a 45-degree angle in that direction. That's the vector u. And let's say the vector v is flat and it goes 3 squares. There's the vector v. If I want to find the vector u plus v, I put u, there's u, and then I put the start of v at the end of u. And the sum vector will go from the start of u to the end of v. This is addition, and one of the things that we like about our addition is for addition to be commutative. Is u plus v the same thing as v plus u? And the answer is yes, otherwise I wouldn't have brought it up. If I draw the vector v, 1, 2, 3, and then at the end of v, I tack on the vector u, I just finish off this parallelogram. So u plus v is the same as v plus u. Tack the end of one, or the beginning of one, onto the end of the other. You make a little parallelogram, and the diagonal of the parallelogram is the sum of the vectors. So if we've got this vector u, which was 2 diagonals worth, if we multiply the vector u by a scalar, we maintain the direction, we just change the magnitude. So if I maintain this direction, and just go twice as far, that will be the vector 2u. So it's made up of one vector. 1u is up to here, and a 2u we like our vector, we like our addition, our multiplication to work together. So it's good to note that 2u is just a u plus a u. So I'm glad things work out that way. Otherwise, we'd have a real mess on our hands here. We multiply by 2. We multiply the magnitude by 2. We scale up the magnitude by a factor of 2. We scale up the magnitude by a factor of 2. This is why we call them scalars. And it's multiplied, so it's a factor. We can also multiply by other things. So if I make it half as long, that's going to be a 1/2 of u. And it is just half as long as the vector u. We've seen already what happens if our scalar is negative. So if I have negative 2 times u, two makes it twice as long. The negative makes it go in the opposite direction. And u is, there would be 1u, and here would be the 2u. But since it's negative 2u, we're going in the opposite direction. Any questions? How's everybody okay? Y'all stunned into silence? I can't tell. I can't see anybody, so. It's hard to see. I have to come up with a picture in my mind of what the class looks like. And so I kind of create this illusion. But the problem is, you know, having seen a lot of movies and stuff like that, I'm imagining classes from like a movie, in which case everybody is just way overdoing what they look like. So like if the director's like, all right, you're really bored in this class, and all my students are like, oh yeah, we're really bored in every class, we don't have to act. But then you start turning actor on, and so you do like super bored, you're like slouching in your seat and your legs are all splayed out all over the place, and you've got this really disgusted look on your face. I gotta tell you, that's not what bored looks like. Bored is like quiet and sitting in the seat just like looking at your phone. But you see it in a movie and it's like all super just splayed out everywhere. It's like, oh, you're bored and you want everybody to know that you're bored because you're an actor in a scene where you're supposed to be bored. Meanwhile, you could just have the teacher be talking about math and the whole audience will understand that everybody is bored. You know what I mean? It's not like you really have to go out of your way to communicate bored in math class. The acting comes in, was like, all right, the teacher's going to be talking about math, and the whole class goes, oh God. And you're like, oh, but you're all excited to hear it. And now the actor's like, oh, ah, yes, a challenge. You know what I mean? All right. Now, right now, notice I was struggling to say, oh, U is kind of going up 2 diagonals going this way, 45-degree angles, and it's that long. So it's kind of a struggle to describe what that direction is. So here's what we're going to do. We're going to imagine vectors in standard position. A vector in standard position will have its initial point at the origin, and then we can mark the endpoints with coordinates. So we can put a vector in standard position where the initial point is at the origin, and then the terminal point will be at coordinates. So we'll have horizontal and vertical coordinates. So the terminal point is at A, B. So in this situation, we're breaking the vector u into horizontal and vertical components. So A would be the horizontal component, and B would be the vertical component. So we can break the vector into components. So if u is the vector with the terminal point at AB, we can indicate what u looks like by using a special kind of bracket. We use these pointy brackets, and then just list the components. Oh, not brackets, brackets. So a common notation would be to use pointy brackets for vectors. Another common notation would just be to put the terminal point in parentheses and call that a vector, and just rely on your reader to be clear from context. But since we're new, we're going to use special pointy brackets to say this is a vector, not a point. Then you show up in my linear algebra class, and I just start listing the vectors, and you're like, well, what happened to pointy brackets? I'm like, I only use those in trig and sometimes in Calc 3. Any questions? Comments? Deep thoughts? Okay, so you can read all about vectors. In the book, we're talking about vectors in section 7.4. So that's what I was talking about today. Let me check. Yes, it's in 7.4. It's in chapter 13 of my in the calculus book. So last time I was talking about vectors, I was like, all right, you can check out vectors in chapter 13. And the students were like, oh, great. And then I got an email. It's like, oh, dude, this book only goes up to chapter 8. So chapter 7, section 4. All right, that's going to do it for today. We'll talk more about vectors on Thursday. Everybody have a good couple of days. I'll see you on Thursday, and thanks for playing.
Thank you.